So we move on now to Chapter 6, Parallel Circuits. And in this chapter, we're going to look at dealing with resistors in parallel, voltage, current. We're going to look at Kirchhoff's current law. We've learned about Kirchhoff's voltage law. And then parallel resistance totals using Ohm's law. Looking at current sources in parallel and how they are different from those of voltage sources. We learned about the voltage dividers. Now we're going to look at current dividers, power, and then some applications of parallel circuits. So all of those objectives there tied to what we just talked about. We're going to look at what is defined as a branch, how a parallel circuit is made up of branches, Kirchhoff's current law, a junction, and the current divider. So when two or more resistors are individually connected between two separate points or nodes in a circuit, they are in parallel with each other. A parallel circuit provides more than one path for the current. So now we're looking at how does current divide up between numerous circuit components. In this case, resistors. The current, of course, flows from the voltage source. In voltage in series, we found that the current remained the same throughout the circuit. Now we're going to find out that the total current is divided up among the branches and each of the parallels circuits that are formed within a simple parallel circuit. So you can see we've got two resistors here. We see how the current divides. We've got four resistors here. We see how the current divides. And of course, what we're going to find out is that the current divides based upon the source voltage and the size of the resistor. So when we look at current in parallel circuits, it can be represented many numerous ways. In this case, it may look like something strange going on, but it's actually just two resistors in parallel. Same thing here, same thing here. I mean, so you have to get used to looking at these circuits and realizing when you have a parallel circuit or a parallel network. If there's more than one current path or branch between two separate points, and if the voltage between the 2 points also appears across each of the branches, then there is a parallel circuit between the 2 points. One of the things that we're going to find out in a parallel circuit, let's go back to this one, is that the voltage across this resistor will be the same voltage across R2. So as we look at this, and you in your lab start looking at, well, how do I build a parallel circuit so that each of the nodes are formed, in this case, all tied together? How would I do that with the breadboard? Well, you can see in this, example here, a typical way that you could do this by separating the 5 resistors out and then tying them back to one node across the top and one node across the bottom, and form this branch, each branch of this parallel network. If we look at printed circuits, you may not have much chance to deal with them, but in a printed circuit, you can certainly see where we have a case of parallel in each of these cases. And so as you go through and identify these, as to how the current flows at pin 1, pin 2, pin 3, and pin 4, as it flows, we have R1 and R2 in parallel, R3 and R4 in parallel, R5 and R6 in parallel, 7 and 8, 9 and 10, 11 and 12. So each of them form a parallel relationship. So in looking at voltage in a parallel circuit, you can see the two examples here. The first one is the same circuit, just laid out a little differently as the second one. All of the points, in essence, are all tied together at the positive pole on this side and the negative pole on this side. So in a representation here of a model, Each one of these is actually the same circuit, just the connections are made a little differently. So in looking at voltage across a parallel network, we can see we've got a 12-volt battery, and we've got 3 identical resistors. And with these 3 identical resistors, you can see we have 12 volts, 12 volts, 12 volts, 12 volts. So in this case, the meter is telling you that you've got 12 volts across each of the resistor. The voltage doesn't change. But what may change is, in fact, the resistor, or the current through each one of these branches at the nodes. So if you look at an example, if we determine the voltage, they want us to determine the voltage across each resistor in this figure. The 5 resistors are in parallel, so the voltage across each one is equal to the applied voltage. Okay, it may not look that way, but when you carefully look at it, you can see that this resistor 3, resistor 4 are in parallel with each other. They're in parallel with 5. All of these are in parallel with 2. And on the other side of the circuit, they're all in parallel with 1. So you have to be careful when you look at a circuit in determining where the parallel branches are in fact formed. So in this case, they just kind of tripped you up here. They threw a little fuse in there. We've got a 25-volt source. Every one of the voltage drops across each one of those resistors matches that of the source of 25 volts. Okay, Kirchhoff's current law. We learned Kirchhoff's voltage law and how we use that to determine the sum of all of the drops has to equal that of the sources. Kirchhoff's current law, often abbreviated as KCL, is often stated as the sum of the currents into a node, the total current, is equal to the sum of the currents out of the node, the total current out. So what's a node? Well, a node is any point or junction in a circuit where 2 or more components are connected. So we saw that in the previous examples. We saw the ones where the 3 resistors were all tied together, node for node, across a battery. So by definition then, we say that the total current then equals the sum of current through branch 1, branch 2, and branch 3. So we can see in this example here, Kirchhoff's current law says the current into the node, so into node A, it divides up into current 1, 2, and 3. Since all of these resistors appear to be of the same value, they will in fact divide equally. They will sum at node B, and the current then will return on its path back to the battery. We can see here in this illustration many currents coming in and many currents coming out of a node. The algebraic sum of all of the currents entering and leaving a node then must equal 0. So you can see it kind of matches that of the voltage law. And so we can look at these long and stretched out examples here of all of the current in, all of the current out. And again, like we did with Kirchhoff's voltage law, we can simplify it by using the summation and saying that all of the nodes from 1 to n then have to equal 0. So this generalized circuit node illustrates Kirchhoff's current law. So in this case, let's take an example here where we break the circuit, stick an ammeter in between each of the paths here, and look at what a physical model might look like. In this case now, you can see we've used 2 different values of resistances, so we would expect the current to be different in each of the branches. So in this case, we can see that through the 3.3 k ohm resistor, we've got 1.8 milliamps, but through the 2.2 k ohm resistor, we've got 2.7 milliamps. At this node, they combine again to form the total current in the circuit of 4.5 milliamps. So if we look at this example, the branch currents are shown in the circuit. Determine the total current entering node A and the total current leaving node B. So in this case, we've got a source, we've got a current of 5 milliamps through the first branch, we've got a current of 12 milliamps through the second. So obviously these two resistors are not the same size. So the total current out of node A is the sum of the two current branches. So the total current into node A then must be the sum. I total is equal to I1 plus I2, 5 milliamps plus 12 milliamps, or a total of 17 milliamps from the source. Okay, the total current entering B then is the sum of the two branches. Again, exactly the same thing. Okay, so in this case, we don't have enough information to solve for the source, but we can certainly see how Kirchhoff's current law is used to determine the total current in the circuit. Okay, again, this is an example, a circuit drawn just a little differently. Can we use Kirchhoff's current law to solve? Absolutely. We've got a total current of 100 milliamps. We've got 30 milliamps in one. We don't know what the current is in two. We do know what the current is, 20 milliamps in three. So we can use Kirchhoff's current law to solve for I2. I2 is equal to total minus I1 minus I3, 100 milliamps, 30 milliamps, 20 milliamps. When we take the difference in those, what's left over is 50 milliamps. So that's the current in R2. Okay. Current sources. Current sources are typically depicted with this little circular representation. In this case, we can see here that actually these are ammeters. Current sources are shown the same way. These are ammeters showing an ammeter breaking into each of the circuits to determine what the current is. So they want us to use Kirchhoff's current law to find the current measured by ammeters A3 and A5. You'll notice neither of those have values given. A1, A2, and A4 have values given, so we can use Kirchhoff's current law again to solve for the currents. So the 5 milliamps minus 1.5 milliamps minus the current A1, A3 has to equal 0. Okay, so solving for current A3 yields current A3, 5 milliamps minus 1.5 milliamps for 3.5 milliamps. So that's the current then at this side between X and Y. So the total current into node Y is 3.5 milliamps. The two currents out of Y, then 1 milliamp through resistor 2, and the current through A5 and R3. Kirchhoff's current law then says the applied node Y current gives us, again, we sum it, let it equal to 0, solve for A5 in this case, so the current A5 yields 3.5 milliamps minus 1 milliamps, or 2.5 milliamps through at the ammeter A5. Okay, so just strictly using Kirchhoff's current law to solve for the unknown, knowing that we have other currents in the circuit and in a branch. Using Kirchhoff's current law, find the current in each of the two tail lights, given that the total current from the battery is 8 amps. Together, the headlights draw 5.6 amps. Okay, so we write Kirchhoff's current law. Current from the battery minus current total head minus current total tail equals 0. So we can solve for I total tail, which is equal to the current of the battery minus the current total at the head. Using the 8 amps that was given minus 5.6 gives us 2.5 amps at current at the tail. Because the tail lights are identical, each of them draws 2.5 divided by 2, or 1.2 amps of current. Okay, we'll go ahead and stop there. When we come back, we'll look at total parallel resistance.